So Alexandre Schubnel works at ENS, and what he likes most is torturing rocks, putting them into a press and listening to their cries.
What an introduction.
Yes.
Thank you very much. Thank you for the organizing committee to give me the opportunity to present the work that we've been performing with a number of people over the last years. I want first to say that I had the luck to study at the laboratory that was where Xavier Le Pichon was working. I never really interacted with him because he was a very imposing figure. I remember meeting him in the elevator many times and saying hello, and he said hello. But one of the things that I really benefited is that from him, indirectly, is that he managed to build a laboratory with Martine Lagache and Claude Froidevaux that actually brought geophysicists, geodynamicists, geologists, and mineralogists all together. And I guess I am the complete fruit of that heritage. And so that's why today I will try to tell you that minerals matter also during earthquake. So when I gave the title Filling Up for Jean-Paul 10 days, about a week ago, I thought I was going to talk about earthquake, and then I realized suddenly that the only other time I gave a talk here was already about deep earthquakes, so I thought maybe I should present something else. And then in the meantime, our colleagues in Japan, our colleagues in Japan have actually just published their work where they showed that so as some of you probably know, there is a large part of the Earth seismicity, about 10 to 20%, that actually happens in the transition zone, and it's been proposed since the 50s that this earthquake may be triggered by the olivine phase transformation. So there is this model where basically you have a cold crust, a cold oceanic lithosphere that actually subducts fast enough into the mantle, enter the transition zone, and being cold enough to remain and to keep metastable olivine. And on the side of the transformation of this metastable olivine core, olivine transformed into spinel, and by some sort of a miracle phenomenon that we call transformational faulting, that actually would trigger earthquakes. So it has been reproduced many times on the analog olivine, so at lower pressure, and our Japanese colleagues just a few weeks ago just showed that this transformational faulting mechanism actually does occur in natural olivine at 20 GPa, so really we are around here. So those are experiments that are mind-bending because they can actually deform small olivines at the pressure and temperature of the down dip of the mantle transition zone while listening to acoustic emission, and they show that this transformation is related to acoustic emission, and this is the microstructure, and you see one of those, this laboratory deep focus earthquake fault here that is filled with the high pressure form, ringwoodite. So I guess this kind of closes, partly at least to me, the debate of whether deep focus earthquakes are actually related to olivine transformation. So I will go talk to you today about deep tectonic tremors, and we will switch on the other side of the subduction zone. So this work is done mainly by Marie Arefé, Pierre Zverev, a colleague in Japan, Seya Yano, and Julien Gasque has been really instrumental. So deep tectonic tremors were discovered after this very short introduction, were discovered about 20 years ago, and it is some sort of a revolution it was a revolution that followed the Kobe earthquake with the disposal of really high, the setup of really high signal-to-noise ratio buried seismometer all across Japan, and Obara-san 23 years ago discovered that in fact they were coherent noise, coherent rumble coming from down dip the subduction zone here. You see the isobat, so the isobat of the slab, so this is 35, this is the Shikoku Peninsula. This is the area that Serge actually has told us, the A, B, C, D, E asperities from Hyuganaga to Tokai. And you see that all the tremors are confined between, sorry, I'm shaking, 35 and 40 kilometer depths. And they are coherent noise. And then a year later, Rogers and Dragert actually showed that they also observed the tremors in Vancouver, so on the other side of the Pacific Ocean. And these were actually also associated with variation in the convergence rate of the Pacific plate. And actually, so plate release, and those were actually slow sleep events. So there was this conjunction between tremors and the tremor rate increase at the moment of slow sleep release. And so I'm just showing you this beautiful animation of the Vancouver and Washington, Oregon, Cascadia range relation between sleep and tremors. This is an inversion that was done by Sylvain Michel and Jean-Philippe a few years ago, and where you see here the variation in the convergence rate, actually. So I think it's the sleep deficit north and the sleep deficit south. When you see that when you have a jump here, you have the tremors, and the tremors actually are associated with those blue zones where basically sleep is accumulated. So there is this transient slips. So so tectonic plate is not this like fixed thing. So the plates are actually moving in a transient manner, in transient slow manner as well. So in Japan, they have unprecedented, really instrumentation of the Nankai zone, as Serge showed. And so this is a VP tomography image here of the tremor zone. So you have the tremor zone here in red. The points here are now on this VP anomaly map. They are in the gray, and then what you see is that they are generally located up-dip zones where you see high VPVS region, and those high VPVS region are generally interpreted as anomalies of high pore pressure fluid, and then those high pore pressure fluid is generally interpreted as high fluid coming from metamorphic dehydration reaction, and so often as the source of fluid, but sometimes also as the fluid migration as a mechanism. And this problem with fluid migration as a mechanism to trigger tremor relates, you can understand that fluid would migrate up dip, but how would it migrate along slip is actually a question. So for the moment, there is not much limited experimental evidence, at least not at in situ PT conditions. And this is now a compilation of the slow earthquake phenomena that was done by our colleagues in Japan, so where slow earthquake in general phenomena have been observed all around the world. And in the places like New Zealand, Nankai, Cascadia, Mexico, where tremors are also observed, in general, we see that there is a high VPVS region. So this is a compilation of subduction zone here, where you see, like in Cascadia, New Zealand, Nankai, Mexico, Costa Rica, there is always, where you have tremors, you also have high pore fluid pressure. So then the last observation, but not the least, is this scaling law. So this is a bit of a difficult plot. So this is how moment is being released during an earthquake. So this is the log of the seismic moment as a function of the duration of an earthquake. And if an earthquake is a circular crack, that actually the moment is related to the cube of its length. And if it propagates at constant speed and constant stress drop, you immediately have the T-cube scaling here. And Satoshi Ide, a number of years ago, realized that it seems that the slow earthquake phenomena do align on a different slope where magnitude is related to time. And there is still a long debate, and in particular, here you see the data of Sylvain Michel, where it seems that in these individual plots here, it could be that the magnitude is also released as cubic duration. So that's now we go to the torturing of rocks. So what can the rock torturing give us some insight about those phenomena? And so I will first show you an apparatus that we've built to reproduce high pressure or lithospheric pressure with acoustic monitoring, and I will show you two examples. One in which we measure P-wave velocity during dehydration, and we extrapolate what would be the VP-VS ratio. And then an example where we think we have recorded tremor-like signals in the laboratory. So the experiment is a rather simple one. You have a machine here which is made of several pistons, and you have a sample which is 10 millimeter long, 5 millimeter high. If you push on this piston, then you actually crush the salt around it, and this salt will confine the sample up to 5 GPa, so around 150 kilometer depth. And then if you push on the central piston, basically you can actually do rock deformation experiment, and you can deform your sample. And while we're doing this, we actually have a transducer. One transducer at the bottom enables us to listen, and the other, and we can also send a wave through the sample and then get it here. And so we can do some sort of a very simple travel time, not tomography, but measure the elastic properties. So this is an example here of the active acoustic monitoring, so measuring the P wave. So we have the source, we have the arrival, and this is as a function of time. And then by performing various cross-correlation, a number of calibration, etc., and the amazing work of RFA, we were able to have to get the velocities as a function of time during the experiment, and then we have the transducer here that enables us to record acoustic emission. So the first part was P-wave velocity. So this is a number of experiments that were performed by RFA and Marie in the last years, where we take a pure antigorite, so from Cape Corsica, actually a rock that I picked up with Laurent, he doesn't remember, but a number of years ago. Actually, so from here, the Col du, I don't remember the name of the anyhow. So this is the antigorite stability field as a function of pressure and temperature. And to make things simple, in this system, antigorite will dehydrate into olivine and orthopyroxene or enstatite, and will release water. There is a small field here where you also have the stable talc phase. And so we take those samples and we bring them into the dehydration domain, so where antigorite is not stable anymore. And while we do so, we measure the velocities. So just to know how the velocity evolves as the rock is dehydrating, and we do so, we go from 300 to the target temperature in a few hours. So this is the microstructure, so that actually tells you that we have a temperature gradient problem in our experiment. So this is as the increasing pressure, 1 GPa, 1.5 GPa, 2 GPa, 2.5 GPa, and you see that the bottom of here has reacted. This is fake colors, I want to say. This is olivine, and here this is the serpentine that has not dehydrated. So the only thing is, by doing thresholding UMHG, we can actually also measure the reaction extent in these experiments. And so if we measure the wave speed, those are the 4 high-pressure experiments. What we see is that as you increase the pressure from 1 to 2.5 GPa, the velocity increases. But as we reach the dehydration point, the velocity decreases. The decrease is very large at low pressure, so we have a decrease from 6.5 to less than 5 kilometers per second upon dehydration here, and you see that that decrease becomes smaller and smaller as we increase the pressure. And we also are now also able to measure the quality factor, and so we see also a very large drop of the Q factor from something around 100 to something around 20. When you look at those curves, what you recognize that they look like sigmoids, so they look like Avrami's law. So Avrami's law is the typical law that actually gives you the kinetics of a reaction, so that at the beginning the reaction is slow, and then it accelerates, and then it's slow again, because there is no more reactant here. And so basically it looks like the VP is a direct measure of the kinetics, and so we can test that. We've tested that, but one of the interesting things is that now, if we assume that VP is a function of the kinetic, we can make a simple model where we simplify the reaction, antigorite gives phosphorite plus enstatite plus water, and we calculate the elastic moduli and the density of solids using a database, and then we use another database for the properties of water. And then we need to decide what is the shape of the water inclusion in the system. And if we were to put the water in spherical inclusion, we wouldn't see any drop in velocities. The only way we can see drop in velocities is that the water that is actually produced during the dehydration reaction has to be embedded in crack-like inclusion, because crack-like inclusion will be very efficient at softening the material. And so basically, it's a little bit counterintuitive that you replace a soft phase by harder solid phase, but because those harder solid phases are actually embedded in a soft crack matrix, basically, you have overall softening of the system. So, and you see that in order to interpret our wave velocity drop, we need aspect ratio, so variation of length versus opening of those cracks of the order of 0.0, 0.05. So we can look in the microstructure, and we do see that, in fact, it's a complete mush, and we have cracks, etc. So it looks that the model is capturing some of the features. But one of the important consequences is that if you do embed the water in a crack-like porosity with a low aspect ratio, you will immediately have very high VPVS ratio, because the shear wavefront will have to go all the way around now those cracks to be able to go through the system. And so you will get a medium with a relatively low VP, but extremely low VS. So it will have an extremely low rigidity. It will not just be softening, but very low rigidity. Okay? So that's an important point, is that dehydration, everybody has this idea that it's actually about like dehydration and brittlement, so you create pore pressure, etc. But in fact, the main thing of dehydration, instead of creating pore pressure, is actually creating a body, a rock, actually, that has extremely low elastic moduli and particularly low rigidity. And rigidity is a critical part of the spring slider model, for instance. Okay, so now we can do, I will show you what happens now if you mix a soft phase, like an antigorite, with a hard phase. And so we've been doing, so Pierre Zverev has been doing experiments where we take olivine powder and we mix it with a little bit of antigorite and then more antigorite. And we do an experiment that is a very simple one. So we just follow a subduction path. So we increase the pressure and the temperature together. And this is very unusual in the mineral physics community. For some reason, people always increase the pressure and then the temperature. And that actually has a problem, because when you do so, you destroy your microstructure, while if you increase pressure and temperature, the pressure compaction effect will be counterbalanced by the thermal expansion effect. So you kind of preserve some sort of microstructure by doing so. And so while we crush those little olivine sample and olivine and antigorite sample, we measure the acoustic emission and we classify the signal. So some signal appear as impulsive, and some signal, as you see, they appear as long duration. So we have just this simple impulsive long duration signal. If we look at the spectrogram, we don't see very much difference between the frequency content, but that's actually because our spectrogram was done on a too narrow window, because there is indeed some sort of low frequency, which is the envelope of those long duration that is not shown here. And what we would like to say is that, of course, this is like some sort of earthquake signal, and this is some sort of tremor signal, okay? But we kind of need to prove it. So one experiment here, this is olivine plus 10% antigorite. So we take it across the antigorite out reaction. And what you see is sorting the signal. We have a maximum of impulsive-like event at at around 300 degree, 0.5 GPa, so which is the down dip of the seismogenic zone. So we're kind of happy. And then, as we cross the antigorite out, we suddenly flipped our seismicity to this impulsive-like seismicity. So we thought, like, okay, this is very nice. We have dehydration-induced tremors. And in fact, then Pierre does an experiment with just olivine, and we have the same. So we don't really need the antigorite to generate the signal. So it actually tells you that the signal doesn't come from the antigorite. It actually comes from the stiff matrix, from the rearrangement of the olivine grains. But however, if we put antigorite, we can synchronize, or more or less synchronize, these zones, these this release with the long duration kind of signal, or the tremor-like signal, let's call it this way, with the dehydration reaction, because the dehydration reaction will create soft bodies that will actually perturb the entire stress field in the system. And so our little olivine sample made of grain will have to rearrange to a certain extent, and it will rearrange in a kind of slow manner, releasing those tremor-like signal. And if we increase the integrite content, we kill there is almost no earthquake-like signal, but we keep the integrite signal. And the amazing thing is that if we do the experiment with 100% integrite, we have nothing. It's completely silent. So it's the conjunction of the two phases. So what we can do, we can measure the B-value. So if we look at the B-value of the earthquake-like phase, we have a B-value of around 1.3, so you could actually say this is earthquake in a volume. If we measure the B-value of the tremor-like signal, it's actually much lower. You could actually question whether it's really a B-value and whether it's really a power distribution or exponential. And so, in fact, in the field, generally, people have described exponential distribution of moment magnitude for tremors, and when they report B-values, they generally report it here as a beta, which is 3 times the B-value, 1.5 the B-value, and they have, our estimates are actually compatible. Another thing we can do, so it's this issue of the magnitude duration scaling. So we take our waveform and we calculate their magnitude. So by simply integrating the waveform, now our sensors are calibrated, so we get true magnitudes. Around magnitude -8, and we can also calculate the duration. So we follow the formulation of Yano and Ide, where we calculate the duration. It's actually hard to calculate the duration of a signal like this, because where does it start, where does it stop? And so what we do is we take the duration, which includes the smallest duration, which includes 50% of the moment release. So basically, that's where the moment release, the duration for 50% where the moment release is the fastest. And if we do this, what we see is that we have our earthquake-like blue signal here that do follow T-cube. So that was actually very nice, because it's been now 25 years that I keep saying acoustic emission are like earthquake, and maybe it's one of the first time we really proved it. And the second thing is that the tremor signal, although it looks like a bubble, a geochemical bubble, or a cloud of points, it does seem to follow this MT signal here. And so in the terms of the Ide scaling, we would be somewhere around here. Okay, so one last thing is that we can measure by approximating the tremor with the Brun crack and calculating with the Brun spectrum and the corner frequency, we can calculate the stress drop of the tremor, and we see that the stress drop of tremors in our experiments are extremely small, of the order of a few kPa. And so if we do that and we take the data of natural tremors, we do have something where the size of laboratory tremor times the frequency of laboratory tremor is about the scales with that of the natural ones, and we're about phenomena that propagate at a fraction of % of the shear wave velocity. And I'm almost done. So yeah, so then we can look at the microstructure. So this is a dehydration zone that is embedded in olivine. And what you see is this very mushy structure where you have the feeling there was a collapse of the structure. And what you see is that next to this collapse, you have these very tortuous crack-like cracks that actually has propagated, several ones. There is another one here. And as you probably know, but tortuous cracks tells you that the crack velocity is actually very, very slow. A fast crack will be a razor-like crack. A slow crack will be a very tortuous one. And so we come up with some conceptual model. This is the only drawing I did in this entire thing, and you see that it's not the best. But anyhow, so you have you have a platelet of integrite which actually dehydrates, and that actually trigger crack linkage along grain boundaries. And if you assume that the tremor is this collective behavior of those crack linkage, you can actually reproduce. This is work done by a Japanese colleague, Yabe and Ujie, where here instead of they have quartz veins, but they can reproduce the tremor signal. And here this is the average tremor spectrum and crack spectrum in our experiment, and where you see there is an increase in the low frequency for the tremors. And I think I've been speaking very, very fast. Sorry. So this is, I will conclude here. So serpentine dehydration is accompanied by low P-wave velocity. I think this is one thing that hasn't been emphasized enough when you look at dehydration reaction. People always think about the consequence in terms of pore fluid, but they never think of the consequence in terms of elasticity. And so that actually, the softening of the material will have mechanical consequence in the surrounding. And so it is possible that when you look at here, you know, if you have this very strong softening of the plate interface here, will have a consequence up dip. And so one of the things is that we do have everything nowadays to measure, to predict the elastic properties of solid plus fluid aggregates at subduction zone PT condition. And this is, I think, something that we should do more. And okay, so we have the two kind of signal, the tremor-like signal and the earthquake-like signal. And I will leave you with the rest of the conclusions. Thank you very much.